Okay. Sorry, I forgot that the sound wasn't recording. Okay, so what I was saying is that we mainly have three types of electrical AC circuits. We mainly have three types of electricity around us. Okay, three modes of our electricity working in different modes. So one of them is DC. Okay, for example, our laptops, phones, etc. uses DC current. Okay, this is basically just 2 volt, a constant 2 volt voltage. Even our logic gates use DC voltages, right? 0 volt means 0 and 5 volts means 1. Transient analysis is whenever you have a sudden change and you have a capacitor or an inductor in your circuit, and that capacitor or inductor gradually changes the voltage and current instead of quickly adapting to the changing voltage and current. Okay, so this behavior is an example of basically storing your voltage or storing your current. For example, capacitors wants to store voltages, whereas inductors wants to store currents. Okay, তো আপনারা যেমন দেখেছেন অনেক সময় whenever you turn off your electrical switch, especially your fan, you might see a spark, right? And that happens because you are witnessing a transient behavior. Whenever you turn off your uh, fan, it might not happen that the fan or the fan that has an inductor inside it, it is not ready to give up that current so easily. It takes a few milliseconds to get rid of that current. Okay, so the current slowly decays. Okay, and the other mode is basically AC, which means basically says that if your voltage or current is, this must be a, first of all, AC current must be a periodic current. Okay, so there is a period involved. Okay, so there is a frequency or a period involved, and a half of the period the wave must stay in the positive side and the other half must stay in the negative side. Okay, that means the average, if you take the average, it is actually 0, right? The average of AC voltage is actually 0. Okay, so since half of them is in 50% of the wave is in positive side and 50% of the wave is in negative side, the average is actually 0. Okay, and you mainly have three different shapes of these waves, and you have seen them in your labs: the square wave, the triangular wave, and the sinusoidal wave. That is the graph looking like a sine wave, right? So we will mainly discuss our sinusoidal AC waves. You will have a frequency involved. For example, the frequency in Bangladesh's grid is 50 hertz, and the RMS average, what does that mean? We'll get to that later. That is 220 volts, but we'll get to that later. Basically, you have a sine wave, say the amplitude is some value A. Okay, and the frequency is 50 hertz, and that means our time period for one cycle. This is just one of the cycles that is being repeated again and again. The time period is 1 by f, which is 1 by 50 second. That is 0.02 seconds, right? So you have seen them in your lab classes as well. Now, what I was saying is that the reason we use AC instead of DC, we use AC to supply this current from our generating sources, for example, from Kaptai or from any other heat generating, electricity generating locations. For example, in Bangladesh, you have a lot of heat generating, heat electricity generator, Tap Bidyut Kendro. Okay, we have a lot of them. For example, in Ishordi, etc. Okay, so what happens is that we use fuel to convert them into electricity. Okay, recently we are having a lot of load sheddings because of that, because the price of fuel went really high and it was hard to maintain the supply of the electricity, right? So this DC electricity is very good for a lot of things, but not good for transferring electricity. Okay, it's not actually good for transferring electricity. What happens is that যেটা হয় যে ডিসি ইলেকট্রিসিটি খুব বেশি দূর সাপ্লাই দেওয়া যায়। Okay, so if we are using electricity for supplying currents everywhere, the theoretical value we will get for the width of our wires would be 1 meter. So আমরা যদি কাপ্তাই থেকে ঢাকায় ধরেন যদি ইলেকট্রিসিটি আনতে চাই, if we wanted to supply electricity from Kaptai, Chattogram to Dhaka, and we use DC electricity, we would need wires that are 1 meter in width. Okay, so মানে আমাদের যদি কাপ্তাই থেকে ঢাকাতে যদি ইলেকট্রিসিটি খালি ডিসি ইলেকট্রিসিটি ইউজ করে আনতে হতো, আমাদের প্রায় 1 মিটার চওড়া তার লাগবে। So you can imagine this would be really unrealistic, right? This would be unrealistic, right? So that is why we ditch DC for transferring electricity. Instead, we were using AC, and you see that the AC wires is very thin, right? The wires going from pole to pole is basically a few inches, and they are made of aluminum. Aluminum is very cheap instead of copper. Okay, so yeah, that is why we use AC. And why is this AC much better than for transferring electricity? Well, the reason is you can use the magnetic capabilities of AC. Okay, so what happens is that we have learned in Faraday's law and Lenz's law that if you change if you change your electricity, if you change your electric field, it will create a changing magnetic field, and that will create again a changing electric field. Okay, but if you don't change your electric field, you get a magnetic field that is constant, and the constant magnetic field doesn't create any electric field again. Okay, that is why we don't. So if you use a DC electricity, you will see a magnetic phenomena, but that will not give rise to another electric field. But if you use AC that is changing, it will create a changing magnetic field, and a changing magnetic field again creates a changing electric field. That means you get AC from AC, and that is what basically transformers do. Okay,
স্যার একটা কোশ্চেন, যদি ম্যাগনেটিক ফিল্ডে কনভার্ট হয় তাহলে কি এনার্জি লস হয় না?
yeah, you may lose some amount of energy. So in this process you will lose some amount of energy, but there's an upside to this. Okay, what is that upside? Okay, যেটা হয়, there is an advantage of doing this. Usually the number of turns of coils in these two sides are not equal. Okay, one side is heavily wounded, and the other side is not. Okay, so if you apply lower voltage on one side, okay, usually on the lightly wounded side, okay, if you apply low voltage on the other side, you will get a very high voltage. Okay, so whatever voltage you apply here, that voltage gets much larger than we supply. Okay, but what happens to the current? Well, since the total power we are sending, the power we are getting from the other side must be equal to that power, or actually less than that, because we have some loss, right? So even if I consider that there is no loss, this power, the V, so the V1 I1, the total power I am sending must be equal to the power we get on the other side. As a result, if the voltage increases, the current must decrease, right? So we are increasing the voltage. We are increasing the voltage. That current must decrease so that it doesn't exceed the maximum the power we have already sent over there, right? So you will get some loss. Okay, you will lose some power. আপনার কিছুটা অবশ্যই lose করবেন, ঠিক আছে? Power যা পাঠিয়েছেন V1 times RE1. We know this is our power, voltage times current. But you will, even if you don't get the 100% of the power, we are assuming that we are getting 100%. Even if you get that, the current must be low on the other side. Okay, so আপনি যেই কারেন্টটা পাঠিয়েছেন তার থেকে যে কম কারেন্ট হয় তাহলে সুবিধা কি? Mainly the reason we needed this large sized wires is that the resistance is very low. Okay, so the main problem we are facing if we wanted to supply from Kaptai to Dhaka our current, the main problem we are facing is that the resistance of the wires is too high for our likeness. Okay, so the resistance is too high. The resistance of the wire is very large. Okay, this is very large. We don't want that. We want a wire with low. Well, we need a wire with low resistance, or what we can do is that we can have a wire with larger resistance, but we can reduce the current because we know that the power consumed by the resistor is I squared R, right? So even if the resistance remains same, if we can reduce the current, the power loss can will go down, right? So basically, you have upside here, right? And you have some connecting wires in between them. This wire may have some resistance, and however much current goes through this resistor or this wire, that will become a loss. That will be lost to the environment. We will never get this power here, right? By the time it reaches the Dhaka, it has already lost P is equals to I squared. Right? So we must reduce the resistance or we must reduce the current. So if we were using DC analysis, the only way was to reduce our resistance. Okay, and the way to reduce resistance is actually to increase the diameter. Okay, remember that R was proportional to L divided by A. So if you increase the area, resistance must go down. Okay, sorry, if you increase the area, resistance must go down. That is one way, but this is not actually the best solution because you will need a lot more material to build this wire. Okay, the better solution is to just use AC and reduce the current. Use transformers to reduce the current, increase the voltage, but reduce the current. That is why in transformers or on electrical poles, there is very high voltages. Okay, even higher than the ones we have in our house. Okay, so in our house we have 220 volts, right? But in electrical poles you have 400 volts, 11 kilovolts. Okay, very high voltages, and even in higher areas, for example, the current centering in industrial areas may have up to 400 kilovolts. Okay, so very high voltages. Okay, but the amount of current is quite low. But if this voltage is very again used, we use another transformer to reduce this voltage down to 220 volt and then use that voltage. Okay, so what happens is that you have what they do is basically you have a transformer that increases the
voice
voltage.
clear
Voice clear. Okay.
So actually
okay, so what happens is that on the Kaptai end, on the Kaptai end, you have a transformer that increases the voltage. Okay, then that and reduces the current. The voltage is increased and the current is reduced, and that is sent over to Dhaka, and there is another transformer that again reduces the voltage back to normal and increases the current back to normal. Okay, then it enters Dhaka, okay, and our houses. And these are called substations basically. So just to use transformers, we need sinusoidal waves or AC waves. Okay, so AC is particularly good for this type of scenarios, and that is why we mainly study AC analysis. Okay, now there is one thing. So you will not need to worry about these sort of things. The main idea is why we need AC voltages. What will be given in exams? Okay, what you have to do in exams is that you have a circuit, just like you had in DC analysis. Just like you have in DC analysis or transient analysis, you will be given a circuit. Okay, you may have resistors, inductors, or capacitors in your circuit. You may have a lot of them. Okay, the only way to look at them is to understand that this is an AC problem, is that the voltage will be given in sinusoidal equation. Okay, so maybe I write it that the voltage here is 10 sine 5t. Okay, and the current here is 2 sine, or maybe also it may also be given in cos. Okay, 3t, something like that. Okay, so the voltages and currents on your circuit, basically every resistor may have some value. So for example, this is 10 ohms, this is 5 ohms, this is 0.2 farads, this is 0.1 Henry, this may be 0.2 Henry, etc. So we will be given a circuit. Since you have sinusoidal voltages, the whole circuit will be operating in AC mode. AC mode. Okay, this is an AC circuit. Okay, so is there anything odd about this circuit? For example, if this problem was given in DC, say this was given just that the voltage of this voltage source is 10 volt and the current here is 2 amperes. Would you be able to solve this problem? So just আমি যদি এই প্রবলেমে এখানে 10 ভোল্ট আর 2 অ্যাম্পিয়ার করে দিই, জাস্ট ডিসি বানিয়ে দিই, এই প্রবলেমে কি এর আগে যা যা দেখেছেন তার থেকে উইয়ার্ড কিছু কি মনে হচ্ছে? ক্যান ইউ সি সামথিং উইয়ার্ড হিয়ার?
0.28.
Okay, not about the values. For example, have you seen any circuit with more than one inductor or capacitor? For example, in transient circuits, I said you will only have one capacitor or one inductor, right?
Yes, sir.
Okay, so আমি বলেছিলাম, first of all, in DC circuits, you don't have inductors or capacitors at all. Okay, you have inductors or capacitors on transient circuit, but I said there will be only one of them. Okay, you will not have more than one transient elements, but here you have a lot of them. Okay, so the thing is, in AC, actually all of these elements, the resistors, inductors, and capacitors basically work like resistors. Okay, they basically work like resistors. Okay, so I don't know about section 4, but in section 3 we saw a lot of graphs in the last class, right? And one of the graphs where the voltage and currents, the voltage and the current of the capacitor, we plotted the voltage and current of the capacitor. And if you see what, if you remember what we saw there, maybe the voltage was something like this, right? And the capacitor's current was something like this, right? And Soumitra sir said that the current here was leading, right? The graph of, so basically this is the graph for the current. Okay, I think I this is the graph for the current of the capacitor. Okay, and the voltage of the capacitor is basically also a sine wave. Okay, that is also a sine wave, except for the fact that both of them are sine wave, but there is a phase shift between them, right? So
Yes, sir.
yes, so basically, when you saw the resistor, and you plotted the voltage across the resistor and the current across the resistor, what you saw is that the voltage, the voltage and the current basically were on the exact same graph. Remember, they
Yes, sir.
were
Overlap.
overlapping on one another, right? So if you apply a sinusoidal voltage on a resistor, the current is also sinusoidal, but there is no phase shift. But for a capacitor or an inductor, if you apply a voltage, sinusoidal voltage, the current is also sinusoidal, except there is a phase shift between the graphs. Okay, so they act like they act very much like resistors, or they act very much similarly, but the only difference is that there is a phase shift between them. Okay, so and you can actually see that. Okay, for example, we know that the equation for resistors is that V is equals to IR, Ohm's law. And if we are looking for the current, we'll write something like this. So if we say, for example, I apply the voltage to be 10 sine 5t, some voltage, and divide with with the value of resistance. Say the value of the resistance is 5 volts. I'm writing the units just so that you understand that these are values I have given you. You will see that the current is basically 2 sine 5t amperes, right? So this is a sinusoid. So the voltage was sinusoidal, and so was the current, right? The current was also sinusoidal, right? But remember the equation for capacitor. I is equals to C dV dt, right? This was the equation for the capacitor. Now, say I give you a capacitor of, let's say, 1 farad, just to make things simpler. And the voltage is actually 10 sine 5t. Okay. So this is just value of 1 farad times some voltage divided by time. You will get something ampere, definitely, because this is current. Okay, some ampere. What happens if you differentiate this? You get 10 times 5 cos 5t, right? You remember that if you differentiate sine, you get cos.
Yes, sir.
Right? So if you apply a sine voltage, you get a cos current, right? So the current you get is 50 cos 5t amperes. So if you plot them on our graph, if you apply the voltage 10 sine 5t, the sinusoid starts from 0, because sine 0 is basically 0. But the cos, so here we have 50 cos t, it will start, the value of cos 0 is 1. So it started from 0. If you guys don't remember, the graph was something like this. So the graph was basically something like this. Okay, so this is the cos curve and this is the sine curve. Okay, and basically the cos curve is basically just a shifted graph. Okay, this is basically a shifted sinusoid graph, right? So that is why we see this phase shift. Okay, and if you want, you can actually write this in sinusoid format because remember, you can write cos like this, So there is, you can directly see that yes, there is a 90-degree phase shift, right? There is a 90-degree phase shift. If you guys remember that sine theta plus 90 degree is basically cos theta. Okay, you might be more familiar with this one, that sine 90 degree minus theta is cos theta, but this is also true. Okay, this is also true, and I think this is better because in this equation both thetas are positive. Okay, on the other hand, you have theta here and minus theta here. So let's worry about this one. Okay, so there is 90-degree. We say that there is a 90-degree phase shift among the equations. Okay, and so this is why basically it acts like a almost like a resistor, except for the fact that we need to change the sign into cos somehow, right? We need to change the or we must remember the 90-degree angle here. Okay, so there is a way to do this. Okay, so basically the job of engineers is to simplify things. Instead of working with sine and cos, if we did this problem in complex numbers, this would become much easier. Okay, so oftentimes you will, in math, you will see that if you go to the higher plane, the problem actually becomes easier. Okay, and there is a beautiful relationship called the Euler equation, that e to the power I theta is equals to cos theta plus I sin theta. You guys are familiar with this equation, right?
Yes, sir.
Right. So this is oftentimes called the most beautiful mathematical equation. Okay. So what it says is that if basically remember complex numbers. So if we have a complex number a plus ib, okay, the way we plotted it was that this point is a plus, say this point is a plus ib. That means the horizontal distance is a and the vertical distance is b, right? So, and we will call this one, this point a plus ib. Okay, geometrically speaking. Okay, and actually, if you use that as if you use polar coordinates for that, you can write that the distance from the origin is r and the angle is theta. The coordinates of this point will be r cos theta, comma sin theta. Also, the a plus ib point here, that also again the coordinate for that point is a comma b, right? So there is a certain similarity in between these two things. And if you take the radius to be 1, okay, so we are talking about all points sitting on this circle, unit circle. So this is, sorry, this is a circle. Okay, the distance is 1. Okay, so we are basically, if we take r equals 1, we see that all of these points are cos theta comma sin theta. Sorry, I wrote sin theta here previously, but that should be r sin theta. Okay, so this point is basically cos theta comma sin theta. And what Euler done is that related to the idea that you can take exponential in complex plane as well. For example, in his mind, I times pi. By the way, this theta is usually written in radians. Okay, I pi would mean that the value is cos pi plus I sin pi. If you guys don't remember, basically pi means 180 degree. Okay, pi radian means 180 degree, and cos 180 degree or cos pi means basically -1, plus I sin pi means just 0. So this gives you -1. So e to the power I pi is basically -1 in his opinion. Okay, so this is basically defined in this way. That this is basically a definition. Okay? But whatever it basically follows more or less all the properties we need in an exponential. So why am I talking about this? Oftentimes you will see that complex number is very helpful, even if you are working with just real numbers. Okay, and just to give you an example, I want to show you one proof. Do you guys remember that sine a plus b is equals to sine a cos b
Plus
plus cos a sine
can
b,
be.
right?
Yes,
This
sir.
formula. Do you guys remember how you proved it? So in order to prove this, you are using, say, this is angle A, this is angle B, and you have to draw a bunch of things. And I don't remember this, but this was a disastrous proof. Okay, this was a very hard thing to prove. Okay, but I will now show you the proof very simply, and you don't have to even draw anything. Okay, so by the definition of e to the power I theta, we will have, if we write e to the power I a, that means this is cos A plus I sine B. Sorry, sine A, right? What am I writing? Sorry, sine A, right? I just replace theta with A. And e to the power IB is basically cos B plus I sine B, right?
Yes, sir.
Confuse any of you. Okay, now if I want to say that okay, e to the power I a plus b. So we know that, okay, so I can write this as e to the power I a plus I b. And we know that e to the power x plus y is basically e to the power x times e to the
Into
power y, right? Basically,
yes,
just
sir.
distribute the exponentials. So e to the power I a times e to the power I b. And we already know the values of e to the power I a and e to the power I b. And if we write it here, cos a plus I sine a times cos b plus I sine b, we'll have four terms. So I'm saying that cos a cos b plus, let's multiply this one with this one, I cos a sine b plus, let's multiply this with this, I sine a cos b plus, finally, I times I is I squared. And what's the value of I squared?
-1.
-1.
Minus 1. By the definition, that I is equal to -1, that is I squared is equal to -1. So I'm replacing that with minus. Okay. And you will see that we have two real parts and two imaginary parts. So I'm writing them using brackets. Right, so this is what we get. So we get a complex number. The real part is basically this thing, and the imaginary part is basically this thing, right? Okay, now again we can write e to the power I theta, right? We can replace the theta with a plus b, right? And what we can write is basically cos theta, that is a plus b, plus I sine theta, a plus b, right? Because this is e to the power, in the form of e to the power I theta. Correct?
Yes, sir.
And from here you can easily see that this is the real part equates with each other, and the imaginary part equates with each other. So that means sine a plus b is equals to cos a sine b plus sine a cos b. And whereas cos a plus b is equals to cos a cos b minus sine a sine b. So you get two formulas with just this one equation, e to the power I theta is equals to cos theta plus I sine theta. Okay, and you get both of them, both of these equations But if you had to prove each of them, you had to do hard trigonometry basically. Okay, so this is how complex number oftentimes uh, makes your problem much easier, especially in the case of sinusoidal and sinusoidal equations. It becomes much easier to use real number and Euler's formula basically. Okay, e to the power I theta format. Okay, so that is why oftentimes we use complex numbers. And for our AC analysis, we will also use our complex number here. Okay. So is that clear what my intention here is? Basically use the power of complex numbers to make our lives easier. That is what engineers do. They don't want to solve the same problem again and again. They want to just basically want a shortcut. We want shortcuts. Okay. And the shortcut I want to give you is basically for solving our problems, for solving our AC analysis problems, what we want is that convert them all of these values into their equivalent complex parts. Okay, how can you do that? For example, let's say this is the problem we want to work with. Okay, so I wrote that 10 volts just to make you understand about AC. Okay. Also, I'm making one more change. I'm changing this cos theta to say cos 3t to cos 5t. So you will have maths like this, and you will have to solve for say the voltage or the current, etc. Okay. So for example, say you have to find the voltage here. What's the voltage of this inductor? So you have that is what you have to find. Okay. So this is the type of problem you will be given. In order to do that, the first step one would be convert to complex. Okay, so what you have to do is basically convert the whole thing into complex numbers, right? How can we do that? Well, there's only one thing. We only care about the amplitude. Okay, so for the voltage and currents, we only care about the amplitude and if there is a theta with it. Okay, if there is a theta with it. Okay, what do we mean by theta? So you see, you have sine here and cosine here, right? This is not what we want. We want something that is exactly same. So for example, I want to solve this problem, everything into cosines. Okay, so the reason mainly is that the real part is cosine. It doesn't actually matter. You can also do this in sine. Okay, but I want to streamline everything. So for this, try to solve everything in cosine. So take if you have something in sine, try to make it cosine. Okay, and how can you do that? Remember that sine theta plus 90 degree is cos theta. Okay, so that means you can also write it like this, that sine theta is basically cos theta minus 90 degree. You can also write this from this, right? So take theta prime. You'll see that these two formulas are exactly same. Okay, so yes, so basically if you want to convert sine into cosines, you basically have to subtract 90. Okay, so you can write this as 10 cos 5t minus 90 degree. Okay, so now both of them are in cos 5t. Both of them has cos 5t, right? So your first job is to, okay, so let's split it from convert to complex. So let's write the step one. Step one, convert everything to cos. convert everything to cos, and what you have to do is just use this formula, that sine theta is equals to cos theta minus 90 degree, right? Just like I have done here, that I have written that tan sine theta is basically sine theta is basically cos theta minus 90 degree. Right. Now, after you have converted into cos theta, the only thing we are interested in the voltages. Okay, convert to complex. The next step is basically convert to complex. So if you have a voltage source or a current source, doesn't matter. If you have a source with the value being say a sine something t plus theta, okay, for example, if you have the values 10 sine 5t minus 90 degree, the complex equivalent will be just the amplitude and this theta. Okay, so the complex amplitude will be 10 e to the power minus I minus 90 degrees, right? Let me, sorry, the minus, I'm writing the minus here. So remember, we have to write the angle here. Okay, let me show you the notations we electricians use. Okay, so electrical engineers like this notation. Remember that e to the power I theta. Okay, so the equation, let me show this equation. So this is our equation, that e to the power I theta is basically cos theta plus I sine theta. But if you have an r, like r cos theta and r sine theta, you just multiply the whole equation by an r, right? And basically this equation is written in this form, that the theta must be in polar coordinates. But you know that we usually use degrees for angles, right? So electricians just write this notation as r angle theta. Okay, because you don't need to write the E, I, etc. Okay, this will be common for everything else. So we just use r angle theta to denote that. For example, here, all we will write is that 10 angle minus 90 degree. Okay, this is a complex number. You can represent the complex number as both with a plus ib format, or you can also write equations, complex numbers in this format. And we are just creating a shorthand for this format. Okay, r angle theta. That is what electric engineers usually use. Okay, we just use the r angle theta, and this is a complex number. The way you want to figure out the value of it is basically 10 cos minus 90 degree plus I 10 sine minus 90 degree. Okay, so basically r angle theta means r cos theta plus r sine theta. Okay, so basically r e to the power I theta. These are basically equivalent keys. Okay, so if you have a voltage source or a current source with a value like this, okay, sorry, I written that everything will be converted to cosine. So let's keep cosine here. 10 cos 5t minus 90 degree. We just write the 10 and minus 90 degree. 10 angle minus 90 degree. Is that understandable? We write the amplitude and then write the angle here. Okay, so tell me, what should be the complex equivalent of this value? Someone please tell me what's the complex equivalent of this 2 cos 5t?
So 2 angle 0.
Yes, 2 angle 0 degree. That's it. Okay, converting to complex number is quite easy. Just 2 angle, whatever the phase angle is written here. Okay, so the
Why 0 degree?
yeah.
Why 2 less than 0? Why 0?
I don't think I can hear you. Let me see.
So he is asking why there is 0 degree.
Oh, 0 degree, because you can actually basically write this as 5t plus 0 degree. That is why. So you basically have a 0 here, like this, right? So we're writing 2 angles 0 degree. Okay.
Okay,
So
sir.
yeah, so basically this is how we write our complex formats of voltage or current source. Okay. Now let's come to our other elements. For example, resistors. Say you have 10 ohm resistor. What's the complex equivalent of this? Well, just 10 angle 0 degree. Whenever you have some resistor, just the amplitude of so the value of R is basically the resistance, and the theta is basically always 0 degree. Okay. So if you have some resistance R, okay, so let me start it in another way. So if you have a resistor, an inductor, or a capacitor with values R, L, or C, okay, so all of these will work like kind of like resistors. Okay, so in AC we give them a common name Z. Okay, that and this is because oftentimes when using complex numbers, we use the number Z for some reason. I don't know, probably because the Germans invented it or something like that. Okay, so whatever, we give the common, we give all of them this common name Z, and we actually call it impedance. Okay, so this is resistance, this is inductance, this is capacitance, and this is impedance. The actual dictionary meaning of impedance is actually just resistance. Okay, so this actually works like a resistance. Okay, so the actual meaning of this is resistance, but you can imagine that this is basically AC resistance. Okay, so if we are working with resistance, the impedance of a resistor is basically just the value of that resistor. Okay, so Z is basically equals to R angle 0 degree. Okay, that actually means just R. Okay, so if you have something, like, so you were some of you were confused why you have a 0 degree here even though you didn't have 0 here. You can try to write it that 2 angle 0 degree, that is basically 2 e to the power I 0 degree, is actually the meaning of it is 2 cos 0 2 cos 0 degree plus I times 2 sine 0 degree, right? And sine 0 is 0, and 2 cos, you will only have a 2 here, right? So basically this is representative of that you have, so the cos 5t part will be absent from your complex number. Okay, even here you didn't have the cos 5t part, right? You will never have the 5t part. Okay, so this is not dependent on the t time. Okay, so whatever. Okay, whatever, what I'm trying to say is that if you have a resistor value, say 10 ohm, the impedance of that will be also just a 10 angle 0 degree, or basically 10. They are exactly same thing. 10 angle 0 degree is basically 10, because 2 angle 0 degree, 2 angle 0 degree is basically 2. Okay, that means this 0 degree means basically that is a real number. So this doesn't matter actually. The interesting parts are the inductors and capacitors. Okay, so the inductor, the value of the inductor is basically Z equals to L angle 90 degree, but you have an omega in front of it. So let me say what's going on here. Okay, so when you have, say for example, this problem, can you tell me what the frequency is? If you actually draw the equation of a sinusoid or a cos wave, we try to write it in this format: a sine some omega times t plus theta. Okay, or maybe cos, doesn't actually matter. If you are working with a cos sign, that's also fine. What is the a here? Amplitude, or basically this is amplitude. Okay, so if you have a cos wave, so have I drawn any cos waves here? So yeah, so the value starts from positive a and goes up to minus a. Okay, so the maximum is a and the minimum is minus a. Okay, so if I write the equation here, like this: cos omega t plus theta. This is how we write it. You have the cos curve here. The red one is the cos curve. A is the amplitude. What we call is amplitude. What we call it is amplitude. Okay. The time is basically the axis t. So that is a variable that is changing from on the x-axis, right? The theta, this theta is called the phase angle. Like we have written the minus 90 degree here. This is actually a phase, or the 0 degree phase. This has a phase of 0 degree. Okay. And what about the omega? So what's the value of omega in this problem? Just match the equation with this the value of
5. Value is
so the
5.
value of omega is 5. Okay, so if you guys remember from your physics classes, this omega is called angular frequency. So you had equations like omega equals twice pi f. If f was frequency, angular frequency was f times twice pi. Right. So for example, in Bangladesh, the value of f is 50 hertz, right? So the angular frequency is twice pi times 50 hertz, which is basically 100 pi hertz. Okay, so this is angular frequency. So whatever, but in these types of equations, you will see the value of omega very clearly. For example, just match the equations here and you'll see that value of omega is basically 5, because you have 5 here, cos 5t here, and also cos 5t here. Okay, so for this problem, the value of omega is basically 5. Okay, this is called the value, the frequency, or angular frequency. The value of angular frequency is 5. Okay, so if I have an inductor with 0.2 Henry and the omega value of omega is 5, what's the impedance here according to this formula? The value of Z is omega L angle 90 degree. The value should be 5 times the value of whatever the inductance is, 0.2 angle 90 degree. Okay, so that means 5 times 0.2 is basically 1 angle 90 degree. Right? Are you guys with me? So this is a formula I'm directly giving you. This is a formula I'm directly giving you. I'm not showing you the proof. You can prove it. Okay, you can prove it. For example, okay, let me show you in the case of capacitors, because I have already shown the equation for capacitors. So for capacitors, the equation of inductance is something like this: 1 over omega c angle, sorry, minus 90 degree. Okay, so this is the formula. So here, if our value of capacitance is 1 farad and our omega is 5, what's the value of the impedance, corresponding impedance? The value of omega is 5 times the capacitance's value is 1 and angle minus 90 degree. This is a formula. This is a given formula. Okay, so you have to only remember these red parts. You only have to remember these red parts. So 1 by 5, you get 0.2 angle minus 90 degree. So this is your capacitance. the corresponding complex number for the capacitance. Now you can just use these numbers like you would for any resistors. So just to give you an example how I got this formula, remember that the capacitances equation was something like I equals C dV dt, right? Now, yeah. So now, if our voltage was basically C times ddt of the, I'm just writing the generic voltage formula like I have written before, cos omega t plus theta, what you would get is basically C times the amplitude comes forward. You have a omega here, so you get that times cos omega t plus theta. Since theta is a constant, there is no effect on this. Okay, so sorry, I forgot to write. Sorry, this should be minus sign. If you differentiate cos, you get minus sign. And using that conversion factor, so I'm just going to write it omega c a. I have a minus sine omega t plus theta. Okay, so remember that you can actually write sine. So I want to convert it back to cos theta. So if I do that, what I will get is basically omega t plus theta minus 90 degree, or is it plus? You have a minus in front. Okay, so something like this, I guess. Minus sign, so cos a stc. I think you should have a plus here, sorry. And if you have that, you can write this, you can basically see this is almost like our voltage, but you have a plus 90 degree shift, right? So when we write that voltage is equals to our voltage with a plus 90 degree shift is basically equals to, so this is voltage angle 90 degree, right? Almost like our voltage. The equation of our voltage is a cos omega t plus theta. So this is just voltage, just add plus 90 to it. You have omega c in front of it, and you have a current here. And if you just write it like this, if you take it on the other side, you will see that you have I times 1 by omega c, and also this 90 degrees on the bottom. So you can also write this as minus 90 on the upper hand. So I'm going to explain it later, don't worry. But this thing almost looks like a Ohm's law, right? This, what I'm trying to get is that this thing almost looks like a Ohm's law, except for the fact this resistance like term, this is almost like V is equals to IR, but except for the fact that this resistance like term, which we call in AC impedance and represent it with Z, is almost like a resistance, but it has a value of complex numbers, right? You have a minus 90 degree angle here. Okay, so this is what I'm trying to tell you guys here. Okay, so you don't have to worry about this proof. So instead, I say that just remember these three formulas. For example, you don't have to even remember the formula for resistance, right? Because the value of resistance is impedance. By the way, the unit of impedance is also ohms. Okay, so basically they're exactly same thing. Resistance and impedance is basically almost exactly same thing. Their value is also equal. But for capacitors and inductors, what you have to do is, for inductors, you must multiply with omega, and then the angle must be, you must have a phase shift of positive 90 degree. Okay, and for the capacitor, you must divide that by omega c. Okay, 1 by omega c times you have minus 90 degree. Okay, so you have a negative shift. Here's a small thing. If you write e to the power 1 over e to the power I theta, you guys know that you can write it as e to the power minus I theta, right?
Yes, sir.
Right. So in our formats, what we can write is something like, for example, this is 2 I theta. So okay, just this can be written as 1 angle theta. So if something you have something that 1 over 1 angle theta, something like this, you have some theta angle on the denominator, you can write it as something like this, that e to the power I times minus theta. So you can write it as 1 angle minus theta. Okay, so if it comes to the top, it automatically gets a negative sign. So that is what I was saying here, that if you divide this side with a 90 degree, so if you cannot understand this equation, what I did is omega c angle 90 degree is equals to V. That is what I have written to match it with the Ohm's law. V is equals to I. Okay, so you have a 90 degree on the bottom. If you take it on the top, you have a minus sign in front. That's what I'm doing here. Okay, so whatever, the proof is not important at all. Okay, what's important is that you understand this is how basically we got it. And this is what you will need. The red parts are what you will need for your math. Okay, so this is how you will convert all of them into their corresponding complex numbers. So let me copy this. We are going to convert this whole thing into our complex numbers. So remember how to convert our voltage sources. This should be 10 angle minus 90 degree, right? Just look at the amplitude and the phase. Ignore the cos 5t part. You have 2 and 0 degree. There is no phase, so basically you have 2 angles 0, right? So for the, now let's look at the RLC elements, resistance, inductors, and capacitors. What's the impedance of this 10 ohm resistor?
0 degree.
10 angle 0, sir.
Yeah, 10 angle 0, or you can also just 10 angle 0 just basically means 10. So you can also write this as well, but for completeness, I am going to write it as 10 angle 0. Z, I'm giving the name of Z1. I think it will be easier if we give this a name. Okay. Okay, so let's call this Z2. What's the value of this inductor?
So 5 angle, no, 0.2 angle 90 degree.
The formula is omega L 90 degree. Okay, omega times L 90 degree. The value of omega is 5 times the value of L is 10 degree, and the angle is 90 degree. So you have 1 angle 90 degree. Okay, Z3. Let's call it Z3. What's the value of this one?
1 by WC.
No, this is a resistor. This is a resistor. I'm talking about the 5 ohm resistor. This is just 5 angle 0 degree, right?
5 angle 0 degree, sir.
Yes, for resistors, the formula is just whatever the value of the resistor is. There is no complex part to that. Okay. Okay. For the capacitors, for the capacitors, I think some of you have your mics.
Last type of the scale. Hi.
Okay, I need you guys to mute if you're not participating in the class. Okay, so now for this capacitor, what's the value of this?
So 1 by 5 into 1.
Okay, let me write the formula first. So always write the formula first.
So 1 by 5 into 0.2.
1 by 5 into 0.2 minus 90
Minus
degrees.
90.
Does everyone agree with this? For the capacitors, you have minus 90. So let's call it Z4. And for finally, for this Z5, the value is, what should be the formula? For inductance, omega L.
W.
This is actually
angle.
okay, the Greek letter omega. Remember, this is not actually W, but okay, whatever. That's not really important as long as you get it right. So 5 times 0.1 angle 90 degree. So you have 0.5 angle 90 degree. Okay. Does everyone agree with these values?
Yes, sir.
Okay. So this is basically how you convert. Uh, convert. Okay. So what I'm going to do is let me redraw this circuit. Okay. Basically, that we have a lot of things here, but what I want to do is clearly draw this circuit with complex values. You have an inductor here. And in fact, I think I oftentimes see that if you give these things names, it is much easier for you to handle. Because of course, the whole course you are not familiar with complex numbers. And of course, you must use complex mode for these types of calculations on your calculator. Okay. But right now we are just doing sample maths, right? So you have the value, and you can write these values here in the value was 10 angle 0 degrees, Z2, the value here was Z2, the value was 1 angle 90 degrees, Z3 was 5 angle 0 degrees, Z4, so the value here was 1 angle minus 90 degrees. Z4 was 1 angle minus 90 degree, and finally Z5 was 0.5 angle 90 degree, and you have 2 angles 0 degree here. Okay, so you can see that everything is right now, everything is a complex number, right? Okay, so this is how we basically convert the whole thing into complex number. And don't forget, we were asked to find the voltage of this. Okay, so if yeah, you can also give names to your voltages and currents as well. Okay. So what now we want to do is basically look at this problem. If you didn't have any complex number, how would you solve this? Basically, forget that you have a complex number here. You have complex numbers here at all. You basically have some voltage source here, some resistor here. So you can treat everything as resistors now, because you have.
So nodal analysis.
Yeah, you can do that. You can do that nodal analysis, of course, you can do that. Right, so this is basically equivalent to something like this. All of them has become resistors, except for the resistors now have complex values. Okay, so don't even worry about them. Just think that the value here is Z1, the value here is Z2, Z3. That is why I gave them names. Okay, and all you have to do is figure out the voltage here. So there are a lot of ways you can do mesh analysis, you can do load analysis, you can do source transformation, whatever, right? So for example, if I also give these things a name, so for example, if I give this V1, or I guess V, and this is I, because we only have one voltage and one current, we can use source transformation to find the voltage. Okay, or we can also do mesh analysis. I think mesh analysis would be great. Because we only have two meshes and one of them is also given here. Okay, I did not create this problem beforehand, so my immediate observation is that if we have two mesh here, so this is mesh 1 I1 and this is I2. What's the value of Bx in terms of I1 and I2? Sorry, Bx. How can I write Bx?
I2.
I2 times
Z5.
Z5.
Z5. Yeah, just think of them as resistors. The value of resistor is Z5. So if you are confused, you can think of it as R5 or something like that. Remember that this is Ohm's law, and this is following passive sign convention. So yes, Vx is equals to I2 times Z5. Right. So all you need to do is find the value of I2 to figure out Vx. And we are also already given the value of I, which is basically this is 2 angles 0 degrees. I am already 2 angles 0 degree. So what's the value of I2?
Minus I.
Yeah. So if this was I, this is basically I, and this is V, I here. I'm just giving them names. So the value of I2 is basically
Minus I.
minus I. And what's the value of Z5? Well, you have already seen that, right? 0.5 angle 90 degree. 0.5 angle 90 degree. And the value of I is 2 angle
2
0
angle
degree.
0 degree.
0.5 angle 90 degree, and if you multiply them, just use calculators, and I think you will get 2 times 0.5 is 1, so minus 1 angle 90 degree. The angles add up, basically 0 plus 90 degree. If you are multiplying them, just use calculators for them. No need to do fancy things like this. Okay, so this is your value for I2 times Z5, or the value of Vx is minus 1 angle 90 degree. Now, here's the thing. You were asked the question, what is the value of Vx here? There was no complex number in this question, right? There was no complex number initially in this question, but in your answer, you gave complex number. How's that possible? Remember that complex number were only just a tool for us. Okay, complex number were only a tool for us to figuring out what the value of or making our computations much easier. Okay, so this is not the actual value. Remember how we converted this voltage, this 10 cos t cos 5t minus 90 degree into some complex number? We now have the exact same thing, but in opposite direction. Okay, by the way, this is in your calculator, you might see this value as 1 angle 270 degrees. This is both exactly the same thing. Okay, this is exactly same thing, so no need to worry about that. And I think this is the proper way to write it. Okay, so this is actually how you see the actual result. Okay, so yeah, so let me show you. I do have a calculator app here. So here, first of all, for this course, for the final exam, you must make sure that your calculator is in degree modes, because electricians, we usually use degree modes, right? We don't even we basically we use degrees for, yes, so no radians for our tasks. Okay, so make sure this is in degree mode. Then let's go to the complex number mode, and if we multiply minus 2 angles, so I'm just going to write this equation here to show you how you will multiply this. So you see that there is a minus 2 angle 0 degree. So how can you write angle? In complex mode, you will see that above this minus inversion symbol, the minus inside bracket, you have an angle symbol. Okay, so press the shift, then press that button, and you'll see the angle pop up. Okay, so minus 2 angle 0 times 0.5 a angle 90 degrees. Okay, so you see the result is given at minus I, right? So this is actually giving our equation in like our Cartesian format, right? A plus IB format, 0 minus 1I. But we actually want our result in polar coordinates. So you will have an system for you to show you the result in polar coordinates in your calculator. So usually it's written like in the format of pole. Say this is, you have a button set for pole. Okay, I think this is not how you see your Casio calculator. Okay, but let me see if I have polar coordinates. Okay, so let's see the result. Okay, did I miss the negative sign? Okay, I missed the negative sign. I'll show you the how to do this in your Casio calculator in front of you. This is a simulator, so this is definitely not how Casio calculators work. But if I press the more button, you'll see that you have 1 angle minus 90 degree. Okay, so that is also one other way to show it, that 1 angle minus 90 degree or minus 90 degree is also 1 to 70 degrees. So it might show up in either way, okay, on your calculator. So whatever, so this is the value of our Vx, but what I was trying to say is that this is a complex number. This is not some actual voltage. So you have to convert it back to your actual question, right? So remember how we converted this, into this complex number. Right now we have to go back from complex number to this format. Okay, so if you are given a complex number that is one angle minus 90 degree, how can you go back to this complex number? What should be the amplitude of this cos something? The amplitude should be 1, right? Then you write cos 5t, and what's the phase? What's the phase? Minus 90 degree. Okay, so basically you only have to write this cos 5t inside of it. And how do we write cos 5t? Well, everything in our problem was in terms of cos, right? So that is why we directly write the cos thing here. And then we have our 5t here, because we also have cos 5t, remember? So that is why your problem must match this cos 5t part everywhere. Okay? So this cos 5t is basically your ticket to converting from this sine cosine into complex numbers. Okay, so whenever you have to convert between complex numbers to this sine cosine, you have to insert this cos 5t, or you have to remove it and insert the angle symbol. Okay, so this is how we do. So for example, here the value is 1 angle 270 degree. That means the actual value of Vx is basically 1 cos 5t plus 270 degree, because you have an inherent plus symbol here, right? So this is your actual answer. This is your value of Vx. So the unit is probably voltage. So I suggest you do the whole thing in SI unit. Don't worry about any other units. Even if you have any other system of units, convert them to SI. Okay, for both transient and AC analysis problems. Okay, is that understandable? So in AC
Yes.
analysis problem, you will definitely face
Sir,
at least
এই
one AC
লাস্টের
analysis problem.
কনভার্সনটা
Okay.
আরেকবার একটু বলবেন যে প্লাস
Sure.
করছি
Last conversion
conversion.
টা আরেকবার বলতেছি. So for example, say after a lot of calculations, you get that Vy is equals to 2 angle 30 degree. How can you convert back to the cosine format? You write the amplitude first.
স্যার হচ্ছে আমাদের
Yeah. হ্যাঁ বলেন আরেকবার।
সার্কিটের যে অ্যাঙ্গেলটা ছিল সেটার সাথে কস অ্যাসোসিয়েটেড থাকবে, অ্যামপ্লিটিউডটা থাকবে, কিন্তু ডিগ্রিটা আমরা প্লাস মাইনাস
Yes.
কনসিডার করি।
So you just have to insert the cos 5t part, and you have the plus 30 here. So this is basically this is what you have to insert, right? So this is definitely we will all we'll be doing all our problems in cosine format. So always use cosine, or if you are actually using sine, use sine here. That's also usable here. But I think this is better if everyone uses cosine. And you have 5t because the problem had 5t at the start of it. Okay, so basically you have to figure out the conversion factor. You can have only one conversion factor, basically cos 5t for this whole problem. Whenever you convert from complex number to cosine format or cosine format to complex number, you have to include this cos 5t part. Okay, so this is your conversion ticket. Okay, this is your conversion ticket that you have to include the cos 5t, and it's done. As simple as that. Okay. Okay, so now in final exams, you will definitely have one AC problem, and that will be similar to this. Okay, so you will have a network of voltage sources, current sources, and resistors, inductors, capacitors. First step is to convert it. So step 1 was convert everything to cosine. Okay, and this cos theta part will be your ticket to your conversion. Okay, then you have to convert it to complex number. Okay, so this cos 5t part is your conversion factor. Now you do just basically simply solve this problem like you would solve any other DC problem. Okay, just solve normally like you would. Step 3 is basically solving the circuit like DC analysis. However you want to do it. If you want to do nodal analysis, that's also fine. If you want to do mesh analysis, that's also fine. You can even apply voltage divider rule, current divider rule, or even source transformations. Okay, all of them are allowed. Okay, so at the end of the this is step 4. Okay, so step 3 is basically this is step 3 that solve the problem. Okay, and after that, oftentimes students forget is that step 4, convert back. Okay, convert back to cos. This is the part students oftentimes forget. Okay, so this is how your AC problems will be presented to you, and this is the type of problems you will have to solve. Okay, the only hard problem that can be given to you is basically this. Let me show you. Let me show you the original problem. I only have a copy of it. Right? So this is the end of this problem. So I have asked you to solve for Px, and you have found the solution. Okay, now. Let's see. This was our original problem. Okay. Now take a look at this. I changed this cos 3t to cos 5t. Okay, I changed this cos 3t to cos 5t, and the reason is that this made the math much simpler. Okay, because what is the conversion factor here? What we did. Let me write it here. So what I did was that 10 cos 5t minus 90 degree. So everything is in cos format. Both of them are in cos. But what is the conversion factor here? Is it cos 5t or cos 3t? If they don't match. Yeah. বলেন কেউ কিছু বলতে যাচ্ছিলেন?
So 5t কারণ ওইটা ভোল্টেজ নিয়ে কাজ করতেছিলাম আমরা।
That's not actually well, what if this was also a voltage? The thing is they both have the equal amount of say in this matter, right? So it doesn't actually matter what this voltage or whether this is the voltage or the current source. Okay, both of them are equally important. Now the problem is we cannot say whether the value should be cos 5t, conversion factor should be cos 5t, or should it be cos 3t. But there is one way. So basically this is applicable when you don't have a matching conversion factor, or the omega is not same. Is the value of omega 5 or 3? That is the question here. Okay, is the value of omega 5 or 3? That is the question here, right? And that is kind of ambiguous because both of them are present here. In this case, what we do is superposition theorem. Remember superposition theorem? Remember superposition theorem?
Yes, sir.
Okay. Why is it? Can anyone tell me how this could resolve this problem?
Sir, আমরা দুইটা থিটাকে কনসিডার করব।
Okay, we will consider both of them. But the thing is, in superposition problems, in superposition, what we did is basically keep one source alive. We kept one source alive and killed every other sources, right?
Yes, sir.
Okay, so for example, this is part one, the voltage part. If we keep this one alive, how can we kill this current source?
স্যার আপনার কথা অনেক আস্তে আসছে।
Okay, কথা আসছে। Saying is if we are doing superposition,
Sir, voice is not disconnected.
স্যার শোনা যায় না।
You cannot hear me? Hello?
স্যার
Can you-
এখন ঠিক আছে।
হ্যাঁ এখন ঠিক আছে।
Okay, so yes, basically what I'm saying is we are going to have this superposition theorem. We have two sources, two independent sources here, right?
আর কথা বোঝা যাচ্ছে না।
আচ্ছা, কথা বোঝা যাচ্ছে না। How can I solve that?
স্যার এখন ঠিক আছে আবার।
আচ্ছা ঠিক আছে, আমি বলছি যে আমরা এখানে যদি সুপারপজিশন থিওরেম অ্যাপ্লাই করি, ডু ইউ গাইজ রিমেম্বার সুপারপজিশন থিওরেম?
ইয়েস একটা
জি,
শর্ট
স্যার।
করে একটা থেকে ভ্যালু।
Yes, so in superposition theorems, we would add up the contributions for each of the voltage or current sources, each of the independent sources, basically, right? We have two independent sources here, and we can say, for example, we are trying to figure out that Vx again. আমরা আবার সেই Vx টাই মনে করেন বের করার ট্রাই করতেছি, okay? এখন what we can do that this is one part of the Vx and this is the other part of the Vx. Say the first bump sided touch, the left side is basically coming from the voltage source only. Okay, so we kill any other source there is. So we should kill this one, right? That would give us the contribution from only the voltage source. And if we had any other independent sources, we'd also kill them. We would keep only one alive and kill everyone else. Okay, রাখবেন একটাকে বাঁচায় রাখবেন, বাকি সবাইকে মেরে ফেলবেন। Often times student make the opposite, creates the opposite scenario. Okay, they kill one and remains, everyone else remains safe, but that's not the one we want to work with. Okay, superposition theorem says একজনকে বাঁচায় রাখবেন, only one of the independent sources will be alive and all other independent sources should be killed. Okay, so if I kill this, how can we kill a current source?
Open circuit.
Yeah, we make them open, right? So this is open, so there is no current through this loop, right?
Yes, sir. No
There
problem.
is no current through this loop, so you can see that if the current is 0, the Vx is also 0, so Vx prime is basically 0. So you don't have any part from this voltage source. Okay, so you don't have anything from the voltage source, so it doesn't matter. You don't actually have to solve this whole thing in complex mode just for this problem, but you may have some other types of problem where you have to solve it. Okay, so this is open. Okay, this is open, and you will just do AC analysis here. Okay, do AC analysis. Do AC analysis and come up with the value. So here, this is just 0 volt. Okay, I don't need to do even any analysis here. And for this side, we should keep that 2 cos 3t part alive and kill this one. How can we kill this one?
Short circuit.
Yeah. How can
So
we
short
kill a
circuit.
voltage? Yeah, short circuit, right? Right. We make them a short circuit. So now, can you tell me what is the conversion factor here on the right hand side?
So 3t.
Yes. See how we do AC analysis here. Okay, and for this AC analysis part, you have omega equals to 3 because you have just killed the omega equals to 5 part. Okay, and on this side, you had omega equals to 5 because that is the only omega you had. Okay, see how we split this one problem into 2 separate problems using source superposition theorem, and we can just use our old techniques to solve our problems. Okay, and you can do whatever solutions you get here. Okay, so for example, the current here is 2 angles 0 degree, and again the value of Vx double prime is basically minus 2 angles 0 degree times omega L. The value of omega is 3 here times 0.1 90 degree. Remember how I solved this problem? I'm just going through them because this is the exact same calculation here, except the value of omega was 5. The value of omega here was 5, and here the value of omega is 3. So if you solve it, we get minus 0.6 angle 90 degree, or this is 0.6 angle minus 90 degree, however we want to write it. And lastly, again, this is 0 volts, right? So this is this doesn't actually matter, but the value say this is 0 angle 0 degree. Okay, just say this might have some other values, right? So I'm just writing this in place of it. So what you have to do again is convert. This is not the actual value of Vx prime. The actual value should be written in cos format, right? What's the value of omega here?
So 0.
No, 5.
No,
The
oh,
value
sorry,
of omega for
5.
this whole circuit problem is 5. The left part is 5. Okay, so you write 5t plus 0, whatever, but then at the end of the day, this is 0. Okay, so I'm not worrying about this, but if you had some other value, say for example 1 and 2 degree, you would write 1 angle something like this, right? This would be your value. But right now here this is just 0 volts, so you would ultimately get 0. So it actually doesn't matter, but still. And on this other side, what will you get the value of Vx double prime? 0.6 cos. What's the value of omega here?
3.
3t, right? So that is the only difference here. Okay, so this is the value of cos 3t minus 90 degree. This is the voltage. So this is Vx double prime, and this is the value of Vx prime. And according to superposition theorem, what's the value of Vx? Just add them out. Okay, so 0 plus 0.6 cos 3t minus 90 degree. So basically, this is the value of 0. Cos 3t minus 90 degree. You may have some other part here, just keep it as it is. Okay, so do you understand the flow of this problem? Basically, convert everything into cos. The first step is that if you have sine, convert it to cos using this formula. Okay, next what you do is find a conversion factor. If you have a conversion factor for the whole circuit, okay, you will only have one conversion factor, cos 5t cos 5t. If it doesn't match, so basically if the frequencies, if you have different omegas, you will have to use superposition theorem. আপনার ওমেগা গুলো যদি ডিফারেন্ট হয়, এক জায়গায় যদি 5 আর এক জায়গায় যদি 3 এরকম থাকে, যেমন আমি লাস্ট প্রবলেমে দেখলাম, তখন সুপারপজিশন থিওরেম অ্যাপ্লাই করতে হবে। This is the only scenario where you must use superposition theorem. বুঝতে পারছেন? এই জন্যই আপনাদেরকে ওই তখন সুপারপজিশন থিওরেম দেখানো হয়েছিল। But the thing is, you could have solved all those DC problems without using superpositions. Okay, but they were just toy models to teach you how to use superposition theorem. Okay, so basically this is the problem where you must use superposition theorem. Also, you may have AC plus DC. Okay, if you have AC plus DC, you can also use superposition to split the AC part and the DC part and separate them, solve them separately. Okay, so you have to you have to convert everything to cos, then convert everything to complex number, then just solve your problem as you would in DC problems, and finally what you have to do is convert it back to cosines. Okay, and if the frequencies were different, for example for this problem 5t and 3t, what you have to do is basically just use superposition to separate them. Okay, to make them into two separate problems where the omegas doesn't overlap. Okay, so you only have one omega part. Okay, so any questions? Is there any part that was like completely out of your bounds, like you couldn't understand anything at all? Is there anyone who couldn't anything at all?
No, sir, বুঝতে পেরেছি।
Okay, so this is basically, this is how you will be presented. This is you will be given a problem like 2 loops or something like this. You will have a AC problem with 2 mesh or something like that, or at most 3 mesh. Okay, but that will be easily solvable. Okay, so yes, for AC analysis problems, this is the type of problems you'll be dealing with on the next class on 30th August. we will have quiz 4 on our transient analysis, and I will try to show this how to solve these types of problems. One more example with how to use your calculators. Okay, and that would be the end of this AC analysis problems. Okay, and I will also show you some problems like RMS value or something like that. So you have seen that the actual average, so the AC waves are something like this, right? You have equal amount of positive and negative values. So if you actually try to find the average, okay, if you try to find the average, you will see that the average is 0. Okay, so there is a better measurement for average here. So for example, if we had say for example, if we had 3 elements, x1, x2, and x3, what does average mean? Well, average means is x1 plus x2 plus x3 divided by 3, right? For AC analysis, if you take, say, for example, 1,000 points, okay, actually you should do integral, but you can also think of it like this. If you take 1,000 points and add them up, you will get 0, because if you have a +2 here, you will see that there is a value -2 here. If you have a value +1 here, you will see that there is a value -1 here. If you have 0.5 here, you will see that there is a negative 0.5 here. So all of them will cancel out. Okay, but so if you find the average of an AC voltage, you will always get 0. So oftentimes average is not a good result. What we do is find the RMS value, which stands for root mean squared. Okay, RMS means root mean squared. How can we find it? Well, first we do squared. So x1 plus x2 squared plus x3 squared. We squared them. Then we take the mean. Then we take the root over. Okay, square root. This is called the RMS value. Okay, this is called the RMS value. This is called the average, and this is called the RMS value. Why is this more useful? Because look at this. If you squared these values, for 1 you would get 1. For 2 squared you would get 4. For 0.5 squared you would get 0.25. But more interestingly, for negative values, if you square them, you will get positive values. Okay. If you square them, you will get positive values. So they will not cancel each other. Okay, so you will get a value. And the value I have said that 220 volt is basically the RMS value of our voltage. Okay, so this is kind of like an average. Okay, but basically the actual average is 0. So this is the term we say this is the average. So you might be able to you might be asked to find the RMS value. So finding the RMS value is very easy. If you have a equation something like this, cos omega t plus theta, whatever the value is, just this is the amplitude, right? And the RMS value formula is given by k over root 2. If you divide that by root 2, that is your RMS value. Okay, for example, this voltage here, if we are asked what's the RMS value of Vx, the value would be 0.6 divided by root 2, whatever that value is. Okay, that might be 0.4 something or whatever. So let's see, 0.6 divided by square root 2, 0.424, right? So the value is 0.424. This is the RMS value. So if you are asked to find the RMS value, just divide it by root 2. That's it. That is the formula. Okay, the formula is amplitude over root 2. That's all. That's all there is to AC. Okay. And yeah, with this I want to conclude today's class. Thank you. This is almost 2 hours.
Sir, quiz 2 এর syllabus-টা একটু আরেকবার বলতে।
Quiz 2, no, quiz 4.
So sorry.
Quiz 4. For quiz 4, transient analysis, just transient analysis. Okay, I'm excluding the AC part. Okay, I'm excluding the AC part. I will give an assignment on AC. Okay, I'll give an assignment on AC, and yeah, I don't think on quiz 4 you will be able to do AC problems because that is just almost like 24 hours later, that quiz, right? You don't even have 48 hours. So yeah, for quiz 4, just do transient analysis, and that is on 30th August during your class time. Please try to come to class as soon as possible, okay? So that we have enough time to discuss our AC and final exams, okay? That is our
অ্যাসাইনমেন্ট আগের যে দুইটা ছিল ওইটা কয় তারিখ পর্যন্ত জমা দিতে পারবো?
ওটা এখনো দেন নাই, so the date was the Thursday. You can still the last Thursday was the submitting deadline, but okay, you can submit your assignments. I'm lenient about the assignments.
স্যার অ্যাসাইনমেন্ট
সাবমিট তো করতে
মার্কস
পারতেছি
কাটবেন
না,
অনেক।
পারমিশন যাচ্ছে,
You guys can't submit it.
পারমিশন যাচ্ছে স্যার ডিসকর্ড থেকে, মানে সাবমিট
The links are supposed to be open, okay?
স্যার ওপেন আছে, আমি ট্রাই করছি।
With your G Suite account.
Yes, sir.
Okay, I will just check the
স্যার অ্যাসাইনমেন্টে যদি ভুল হয় তাহলে কি অনেক বেশি মার্কস কাটবেন?
বুঝতে পারি না কি
অ্যাসাইনমেন্টে যদি অ্যানসার ভুল হয় তাহলে কি অনেক বেশি মার্কস কাটবেন?
cannot understand this, sorry.
আস্ক করছে অ্যাসাইনমেন্ট অনেক ভুল হলে মার্ক কাটবেন কিরকম সেটা?
অনেক ভুল না, বলছি
অ্যাসাইনমেন্টে আমি তো আপনাদের সলিউশন দিয়েই দিব, ওকে? সো অ্যাসাইনমেন্ট you can, if you are worried about marks, just ওইটা দেখেই করেন, but the point of assignment is to actually teach you how to solve those problems, because I usually try to maintain similarity between your quiz questions, final exam questions, or mid-exam questions with your assignments, okay? So solving these assignments will actually give you some order of confidence, okay? So yeah, if you are worried about the marks in your assignments, you can just will give the solutions one day before the submission deadline. So I have already given the solution for assignment 1 and 2 in Google Drive. You can see that, and I will also post the links if they're not open right now. I'll actually check them right now and I'll actually open them. Okay, so don't worry about the deadlines, but last Thursday deadlines. But you must submit everything by 6 September, right? Is this September? Yeah, by 6 September. I will have to aggregate all the marks, so please complete it by then.
Yes, sir.
So all the assignments are due by 6 September. Okay.
Thank you, sir.
So I will post it right now. Check the links
স্যার
again.
আবার কি সাবমিট করা যাবে অ্যাসাইনমেন্ট টুটা?
If you have already submitted, it's fine, and I will give another assignment 3 for AC analysis, okay? But if you have already submitted once, you don't have to submit again. Okay, if you have already submitted
sir.
once, why would you have to submit it again? This is for submitted assignments, okay? Okay, so
থ্যাংক ইউ স্যার।
স্যার ওয়ান মোর কোয়েশ্চেন।
yeah, sure.
স্যার এই লেকচার ভিডিওটা স্যার হচ্ছে কখন আপনি পোস্ট করবেন আবার
I will
ডিসকর্ডে?
upload it right away.
স্যার
Just after the conversion completes, it will take some time because 2 hours video recording will take some time to convert it. But after it's done, I will upload it. Okay, and I'll post the links as fast as possible. Okay.
জি স্যার।
Thank you. Anything else?
Bye, sir.
Yeah.
স্যার আসসালামু আলাইকুম।
Walaikum assalam. So section 3, meet you tomorrow, and section 4 we'll see on Tuesday.
আসসালাম স্যার।
Walaikum assalam.
Thank you, sir.
Hello, second.
Welcome, sir.